In section 7.4, we're going to talk about how to make a confidence interval. You've probably even seen confidence intervals before. If you look at any news reporting, a lot of times they actually say that a certain percent of people have some characteristic, and they might give like a plus or minus 3% or 4% that goes along with it. That's what we call the margin of error, that 3 or 4%. Because we know when we take a sample, we won't necessarily always get the true population proportion, that it could vary for a little bit from sample to sample. So we're going to talk about how we find that, how much do we think our sample proportion varies by. And it's actually based on two things. It's based on your sample size. Remember, the larger your sample, the less variability you're going to get in your sample proportion, so you can get closer to the true value. And it's also going to be based on how much confidence that you want. Okay. So a confidence interval for a population proportion is an interval of values computed from sample data that is almost sure to include the true population proportion. Okay, so it said it's almost sure. So that's the key, is we can't be 100% sure. We can just be almost sure. Kind of like that M&M example that I did in the end of the last section. Okay, we came up with our interval didn't include what we found posted online, but we're not sure which is right, what's posted online or what we use for our interval. Okay. The most common confidence interval that almost everyone uses exclusively, except for some extreme circumstances, is normally just a 95%. Okay. So what we do is we actually base the 95% on the process that we're using. So the process that produces this interval captures the true population parameter with a 95% of the time. Okay. We can't say that the interval includes the population proportion 95% of the time. We're just saying the process that we use, okay, captures the true population proportion 95% of the time. Okay, so the population proportion is a fixed number. It's either in the interval or not in the interval. We can't associate a probability with whether or not it's in the interval. Okay, so if you remember back to the empirical rule that we talked about, okay, for a normal distribution, about 95% of the data is within 2 standard deviations of the mean. Okay, so go back to our central limit theorem. Right, we know the sampling distribution of sample proportions is a normal distribution, okay, and the standard deviation is calculated using this formula. So combine that together with the empirical rule. Okay, I know that my proportion will be plus or minus 2 of these standard deviations, and remember, if I go 2 below the mean and 2 above the mean, I'm going to have 95% of my data. Okay, so but in this case we're talking about sample proportions is what my data is about. Okay, so this is the population proportion. So if I take the population proportion, which should be the mean of my sampling distribution, and I go 2 standard deviations on either side of it, by the empirical rule, that means I'm going to capture about 95% of the data. Okay, so about 20 million Americans attend college each year, and about 12 million, or 60%, borrow annually to help cover costs. So if many random samples of 500 American college students were surveyed about college debt, what would be the mean and standard deviation of the sampling distribution of the percent that borrow money to attend college? Okay, so again, we're not building a confidence interval yet. We're just making sure that you understand the central limit theorem. Okay, so the mean of my sample proportions is the population proportion, which is 60%. Okay, you can pull that right number right there out of the problem. Okay, and the standard deviation of this, or what we call the standard error of the sampling distribution, is this formula here. So we're going to put the 0.6 in for the formula, and you should get out on your calculator 0.022, but again, I can convert that to a percent, so it's 2.2%. Okay, so I know by the central limit theorem that I have a normal distribution with a mean of 60% and a standard deviation of 2.2%. Okay, so if I take many random samples of size 500, right, then 95% of the sample proportions are going to be between 55.7% and 64.3%. Okay, I'm getting these numbers because I'm doing this: 60% plus 2 times 2.2 and 60% minus 2 times 2.2%. So that gives me a lower bound of 55.7 and an upper bound of 64.3. Okay, but this is working backwards from the way we usually do it, because normally I don't know the population proportion. I know a sample proportion. So I have to build my confidence interval around a sample proportion, and then I say that I'm 95% confident in the process that I'm using, so I'm 95% confident that my population proportion is going to be in this interval I build. But again, I have to do it for a sample proportion, because if I have the population proportion, there's no reason to even take a sample. Okay, so most of the time we don't know it. Okay, so if I take a random sample of 500 American college students, okay, I can calculate the sample proportion. That's just how many have college how many have college debt divided by the total people in your sample, and we can use the sample proportion to find an interval that contains the population proportion. So just for instance, let's just suppose that 58% of my sample has college debt. Okay, so I can use this. Remember, within 2 standard deviations give me 95%. So I want to make a 95% confidence interval just by plugging my 0.58 in for p hat. Again, I'm using p hat now because I don't really know what p is. Okay, so I come up with 0.58 plus or minus 0.044. Okay, so now if I do 0.58 plus the 0.044, that gives me my upper bound, and 0.58 minus 0.044 gives me my lower bound. Okay, so I can actually read this if you want as 53.6% up to 62.4%. Okay, so we are 95% confident that the proportion of American college students that borrow annually to cover college expenses is between 53.6% and 62.4%. Okay, so if we took many samples, they all have to be the same size, so all of them have to be size 500 from this population. 95% of the samples will include the population proportion. So do I know that my interval includes the population proportion? I don't really know. All I can do is say that I'm 95% confident that it does. Okay? But don't say there's a 95% chance that the population proportion is in this interval. Okay? I'm just saying that this is an interval I calculated, and I'm 95% confident in the process that I did. Okay, so your confidence interval is built up of an estimate and a margin of error. Your estimate for proportions is always the sample proportion. If we were to do for sample means and trying to estimate a population mean, my estimate would be the sample mean. Okay, but that's the chapter in the book that we're not doing. So for now, we're only working with proportions. So my estimate is a sample proportion, and the margin of error is based on the confidence level and the standard error. Okay, so we have what we call this Z star, and Z star will change depending on what confidence level you want. So you see it right here in the formula. Currently, we've been using 2 because I've been talking about a 95% confidence interval. If I wanted to make a 68% confidence interval, then I would make my Z star 1. Remember, the rest of the empirical rule says that 99.7% fall within 3 standard deviations, so I would make this a 3 here if I wanted a 99.7% confidence interval. Okay, so this piece here is the standard error. If I multiply it by this Z star, this piece all the way starting here, right just to the right of the plus or minus, this whole part here is what we call our margin of error. And then the estimate is the sample proportion. Okay, so far we've been using 2, but 2 is actually kind of just a rounded off number. Okay, so if you use the table that's in the back of your textbook, okay, what we're really looking for is where 95% fall here in the middle. If 95% is in the middle, then I have 5% for both this piece in white and the piece in white over here. Okay, so if I divide that 5% that's left by 2, because it's split evenly between the two pieces, I get 2.5%. So what I can do is I can go look in the standard normal table, change that back to a decimal to 0.025. Okay, and you say, oh, there it is. And if you read the z-score that corresponds to that, it actually shows up as negative 1.96. Okay, we're actually going to use positive 1.96 because the whole thing is symmetric. So right here we are at negative 1.96. Here we are at positive 1.96. The reason I don't have to worry about the negative sign is because of the plus or minus that's in front of the formula, in front of your z star. Okay, where before we started out using 2, I've actually made my multiplier a little more exact. I now made it 1.96. Okay, Okay, so all I'm going to do is in my formula is change where I was using a 2 to 1.96 if I'm doing 95%. Okay. Now what's Z star if you're doing 90%? So again, you'd have 90% in the middle. Remember, the 90% represents the proportion of sample proportions that would fall here. 90% of them would fall in this area. Okay. Okay. In our empirical rule, we would say the answer would be 1. So I have 90% in the middle, 10% left for the 2 pieces in white. Divide that by 2 and I get 5%. Convert that to a decimal, I get 0.05. So I'm looking for 0.05 in my table, and I don't find it exactly, but I do find it that's actually halfway in between these two values. So I'm halfway between negative 1.64 and negative 1.65. So halfway in between there is negative 1.645. Again, I'm not going to use the negative sign because I actually have a plus or minus in the front. So we're actually using both negative here and the positive there. Okay, so let's go back to my M&M example. Okay, so this time I'm going to take a sample of 100 M&Ms. Okay, and when I count these, I find 11 yellow pieces. Okay, now before I start doing this, we actually should check that the conditions work for the central limit theorem, that I select them randomly, the independent. I have a large sample, in this case 100. Remember that you have to take is 0.11 times 100, because that would be my p hat, greater than 10, and yes it is, and is 1 minus this number times 100 greater than 10. Yes it is. So I have a large sample and a large population because there's lots of M&Ms out there. Okay, so I find my p hat. It has 11 pieces out of the 100, so it'd be 11% or 0.11. Remember to always use decimals in your formulas when you're doing this. Okay, here's my formula. Okay, I'm finding a 95% confidence interval, so in my formula I'm going to put the 1.96 in for the Z star. So p hat is 0.11 plus or minus Z star, which is the 1.96. And again, I'm going to use p hat as 0.11, so 0.11 gets put in for my p hats. My sample size is up here at 100, so I'm going to be dividing the whole thing by 100. If you calculate just this piece, which is my margin of error, I get 0.06. So I actually have a 6% margin of error. Okay. Okay, so what I can say is when I calculate this, we are 95% confident that the proportion of all M&Ms that are yellow is between 5% and 17%. Okay, now I actually found a website that claims that the number of yellow is 20%. Okay, if you remember my interval, it went from 5 to 17, and 20 is not in that interval. So I have two things that could happen. Either this 20% on the website's wrong, or we have a bag that's in the 5% of the samples that didn't capture the true population proportion. Okay, I'm not sure what happened. We have no way of knowing. All I can do is say we're going to talk a little bit more about this in chapter 8. Okay, so when you do this, you're never positive whether or not you actually have the true population proportion in your interval. You can just be 95% confident that you think you do.